Well, hello, we're talking about the atmosphere this chapter, and let's get going. This seems to be a long one. So here are the learning objectives for this section, and here are the layers of the Earth's atmosphere. So we have the troposphere. This is where we live in troposphere, and the layers of the atmosphere are denoted by their temperature profiles. So as you go higher in altitude in the troposphere, the temperature goes down. The between the troposphere and the stratosphere, we have an area called the tropopause. And then in the stratosphere, as you raise in the stratosphere, it gets hotter. So this is the opposite of the troposphere. Of special interest, there is an area called the ozone layer, and this protects the Earth from ultraviolet light, specifically ultraviolet B radiation. This is the radiation that causes skin cancer and sunburns. And then the mesosphere. Okay, so then between the stratosphere and the mesosphere is a stratopause. Then you have the mesosphere, and this has the same temperature profile as the troposphere. And then between the mesosphere and the thermosphere, you have the mesopause, and then you have the thermosphere. It has the same temperature profile as the stratosphere. The in general, as you go up, the the atmosphere gets thinner. And then you have the exosphere that's outside of that. That's on the order of 60 miles above the surface of the Earth. And the layers of the Earth, the atmosphere, they change. So it's not like there's a general area where they lie, but they can change day by day. It just depends. And here's the temperature profile. So if you look here, you have the troposphere. That's where we live, and the temperature profile. The higher you go, the cooler it gets, and then the temperature profiles change on the differing levels of the atmosphere. And the altitude, it depends. It truthfully depends, uh, day by day, where each of them are they lie. And okay, so what is the atmosphere made of? So this is dry air. So depending on where you're at, the atmosphere has more or less 1% or so of water. Of course, in really humid places, it's higher in water, and you have really dry places like deserts, it's less water. But dry air is about 78% nitrogen, about 21% oxygen, about 1% argon, and 0.4%, 0.04% carbon dioxide, and trace all else. And they're the trace gases. And nitrogen is a large amount. It's a fairly inert gas, and it's important because and plants need it as a macronutrient, but it's not usable in its form. It needs to be fixed. So there's a couple ways you can fix nitrogen, and one of them is lightning, and that does it. There's also symbiotic relationships with cyanobacteria. So cyanide, carbon, nitrogen. So cyanobacteria will fixate nitrogen as well. So it doesn't have to be lightning, but that we can do this artificially using something called the Haber-Bosch process. And I've done research on this. I did research on the catalyst in grad school, so I've done I know quite a bit about this. It was around the year 1900. The population of the Earth was approaching 2 billion, and the population had grown past the point that we could feed it. And this is known as a Malthusian catastrophe. And the leaders of the world, well, we were mining nitrates in Chile and using that to grow crops, and it's not a very sustainable process. So leaders of the world were like, we need to do something, and they turned to the chemists to help them. And I don't think Haber did very much. Actually, I don't like Haber that much. If the people that you meet in your life, he's someone I think I'd rather punch in the face than have lunch with, to be quite honest with you. He was a German. He was also Jewish. Not that that really matters, but he he's also the one that invented chemical weapons. He suggested that the Germans used chlorine in World War One. And he would go around dressing in his military uniform. He considered himself to be a great soldier, but later on was felt a bit of guilt for it. I guess a little redeeming. But he was an academic, and he figured out he could make ammonia with using osmium. Osmium is more expensive than gold, so it's not a very usable process. Carl Bosch came around. He worked for a company called the BASF. It's still in in around. We still have the BASF, and he figured out how to deal with hydrogen, high pressure gases, and he also figured out how to use a catalyst. The catalyst he used, he took iron ore from Sweden and heated it up for 2 days in the presence of hydrogen, and then he made a catalyst doing that. How he figured that out, I have no freaking idea. He tried a bunch of different catalysts, it's like Thomas Edison and the light bulb kind of idea, but he more or less by trial and error, he made a usable catalyst, and that is still the catalyst we use today. We don't need iron ore from Sweden. The Swedish ore had impurities of aluminum and potassium in it that made it special. So we can mimic that. We don't need Sweden anymore. But that led to ammonia synthesis, and after the Germans had that, you can take ammonia and you can burn it to make nitrogen oxides, and you can mix that with water to form nitric acid. If you have nitric acid, you can make explosives. So, like TNT makes is trinitrotoluene. So the way you make TNT is you take toluene, you mix it with nitric acid. Nitroglycerin, which is used in dynamite, that is you take glycerin, you mix it with nitric acid. So nitric acid is very dangerous, and it's a controlled substance. So, but that allowed Germany to fight World War One. So after BASF started making ammonia, they started making nitrates, they started making explosives, and then World War One broke out. So chemists came around, and we helped prevent the worlds from starving, and we also gave it the way to have massive warfare. So they thought World War One was going to be easy. They put a blockade. The British Navy put a blockade on the German boats and say, all right, well, no more nitrates for them. They'll just run out of food, and they were making all the ammonia they needed. So they didn't starve, and they could make more explosives. So, but we still use the same process today, and sometimes we use different catalysts. There's better catalysts than the iron catalyst. You can use well, it doesn't matter. It's beyond this course, but we still basically do it the same way. And now we had all the nitrate we wanted, so we now can have all we have this huge population boom because of the synthetic fertilizer, and basically the crops that we grow today are crops. I mean, kind of, if you will, on steroids. They are that we produce so much more food than we did in the past, and that's the reason why we have the population that we do now. Well, one of the reasons. Uh, I mean, there are various reasons besides that. Actually, in some ways, we have so much food that we are getting fat. Uh, I mean, there are other reasons why we have a huge population. Another reason is medical technology, specifically antibiotics. Antibiotics have prevented infectious disease deaths, or a majority of them, and so more people will have lived to sexual maturity and reproduced. And what's killing us now, besides accidents, but like most of the deaths are from cancer, cardiovascular illnesses. That's the slow killers. That's what generally kills people nowadays. In the past, it was mostly from infectious disease. So we got lots of food, and we live long times, and we have lots of kids. So that means we're going to have a huge population, and we're still growing. And we have this and because of science. Okay, so here's the nitrogen cycle, then the natural nitrogen cycle, the atmospheric. Well, I guess we can fixate it with ammonia fertilizers, but it comes from lightning and bacteria. So bacteria can fixate it, lightning can do it, and also bacteria can denitrification as well, and has a cycle like that. Oxygen cycle, so this is done by photosynthesis, and of it, the majority of it comes from algae. And interestingly enough, well, the first, well, after plant life happened in the on the Earth, the atmosphere did not accumulate oxygen for about 1 billion years, because the oxygen just went and reacted with anything that was around on the surface. It took a long time for all the oxygen to react with everything on the surface, and then it started to accumulate. And now, of course, we have quite an accumulation of oxygen. And this is one of the things we're looking for life and other objects. We're seeing if there is an oxygen atmosphere, a thick oxygen atmosphere. So if you look at the atmosphere of Mercury, for instance, the planet Mercury around the sun, it's 35% oxygen. But that oxygen just comes from the radiation of the sun just baking and hitting in the rocks, releasing oxygen from Mercury. And the atmosphere is very thin. So there is, as far as we can tell, there's nothing living on the surface of Mercury, at least not plant life. But on the on other worlds, though, we were going to see if we can find a significant amount of oxygen in the atmosphere. If we do, then that would suggest that, when I say oxygen, I mean O2 gas. That would suggest living creatures. And also in the stratosphere, we have ozone. And the nice thing about ozone is it absorbs ultraviolet radiation. And well, with ozone, as long as the sun is shining and there's oxygen in the atmosphere, we're going to have an ozone layer. Unfortunately, there's an ozone hole right now. Well, not a complete hole, but a partial hole over the Antarctic. And more ultraviolet light is getting through. If you've ever been to New Zealand, I'm a very fair complexioned person. You have to wear a lot of sunscreen because you can get sunburnt there very easily from the ozone hole. Okay, so a temperature inversion, and this is certain places. Most places you have warm air on the bottom and cold air and cooler air on the top. Problem is if you have a temperature inversion where you have where the above band is warmer, you can get pollutants trapped in there. Los Angeles, for instance, has a temperature inversion. Mexico City has a temperature inversion, as does Cincinnati, Ohio, my hometown where I was born, has a temperature inversion. And then in these situations, pollutants get trapped underneath there. And well, there's not as many people. I mean, a mere 2 million in Cincinnati, but Los Angeles has many, many people, and you can have the photochemical smog form there. We'll talk about photochemical smog later, and this is pollution can be very difficult for these areas. There's always been pollution. Much of it is natural. I mean, living in Hawaii, we have the volcano. The volcano spits out lots of pollution, and many of them natural sources. There's dust storms, for instance, that can create pollution as well. And then there's pollution on Mars. There's dust storms on Mars, for instance. And we've always had pollution. Much of it is natural, and we've altered our environment. And we've impacted land and our atmosphere with pollution. And what is pollution, though? Pollutant is the wrong place at the wrong time. And air pollution has become a concern. So most pollution, though, is local. Though there's the pollution usually stays local. The only one that's really global is carbon dioxide. So industrial smog. There's common names for this. London fog is another one. It's a combination of smoke and fog. Mostly sulfur dioxide and particulate activity. Particulates. So what is particulate? Particulates are tiny particles. So when we burn carbon, it produces, among other things, soot. So like if you've seen smoke coming out from a fire or a candle or something like that, this unburned carbon is soot. That is a particulate. They're tiny particles. And also sulfur dioxide. Sulfur dioxide is included in this. And sulfur dioxide is oxidized to form sulfur trioxide, and then reacted with water to form H2SO4, sulfuric acid. So the industrial smog also can contribute to acid rain. So Acid rain is denoted as any rainwater lower than a pH of 5.6. So particulate matter, this is solid particulates that form. So fog, for instance, that we experience in Hawaii is particulate matter. And the fog, depending on where you're at, it's typically ammonium sulfate is the particulate matter that we see in Hawaii. It can also be particulates of sulfuric acid as well, but it's primarily ammonium sulfate. Uh, Other places, though, it depends on what it is. It could be sulfuric acid, it could be ash. And the EPA, Environmental Protection Agency, estimates that 40-some thousand people die because of particulate matter. And it's a range, though. So really small particulate matter can be absorbed in the bloodstream. Really large particulate matter doesn't make it to our lungs, but a medium size can get into our lungs, and that can cause issues with your lungs. That if and your lungs do clean themselves, but over time you can gunk up your lungs with particulate matter. So types of smog: winter smog, sulfur smog, London smog. Here we can call it VOG. And then there's photochemical smog. We'll talk more about photochemical smog later. For industrial smog, sulfur dioxide and particulates, just like the volcano makes for us. And then photochemical smog comes from nitrogen oxides and hydrocarbons. And forms industrial smog forms acid rain, and photochemical smog forms ozone, aldehydes, and peroxyacetyl nitrate, or known as PAN. Source for industrial smog is power plants, basically coal, a lot of coal burning stuff, and the cars are the similar, or transportation, internal combustion engines are the source for photochemical smog. Weather tends to be cold, damp. Of course, we get the fog here in Hawaii, but it seems to affect places more that are colder and damp, like London. So and then photochemical smog tends to be the warmer climates, like Los Angeles. Okay, so for industrial health and human health hazards for industrial smog, so human health, it can damage the lungs. So, and environmental can cause damage to plants. So, in Hawaii, we have terrible acid rain, but the plants have evolved to deal with that acid rain. Uh, in areas of the country where it doesn't have acid rain, suddenly there's acid rain from from human sources. It can really damage the plants. So acid rain, you wonder, why does acid rain, if it's such terrible acid rain, why is it not a big deal in Hawaii? Well, it's because the plants are used to it. Whereas in the mainland, if there's acid rain, in other areas of the earth, of course, not just the United States of America, that can really damage. A sudden increase in acidity of the rain can damage the crops that are there. Also, it can damage human monuments. So gravestones. If you want to go to a graveyard in Hawaii and look at the stones, you can see how much corrosion can happen from the acid rain. So how do you prevent industrial smog? You get rid of the particulate. So you can use an electrostatic precipitator. This will use electricity to charge the particles and take them out that way. Bag filtration, kind of like an old school vacuum cleaner. Cyclone separator can cycle they use a spherical motion to trap the particles. Wet scrubber, so just kind of run water through particulates and through a stack. You typically stack the stack with usually kind of like, they look like the ringed pasta, usually made of plastic. And you can also wash coal. This is a remediation. Wash coal or add limestone to it to make it burn a little more cleanly. So that's like a preventative measure before you burn the coal. So automobile, gasoline is a mixture of hydrocarbons. Depends on the state, depends on the country, what that mixture is, and we usually use octane, and but it tends not to completely burn. So incomplete combustion, carbon monoxide is formed. Carbon monoxide is poisonous, and it is really poisonous. And one of the ways we can get it down though is using a catalytic converter. So carbon monoxide is a poison because it binds with hemoglobin, and it binds more strongly than than oxygen. And nitrogen oxides, when in the internal combustion engine, that heat can form nitrogen oxides, and those nitrogen oxides can then eventually turn into acid rain. So there is a natural form with electricity with the lightning bolts. Lightning bolts. So the Earth does this naturally, of course, but uh, this is tends to be a steady state. A sudden increase in acid rain can cause damage to crops, not all crops. Actually, acid rain sometimes can help crops, but the plants that are around that are not used to it. With crops, we can sweeten the soil by adding lime to it. So there's ways to mediate this, but it's a little harder to mediate the effects of the entire biosphere. Okay, and volatile organic compounds. This can also lead to smog. You need sunlight as well, so VOCs and sunlight. So we need decreasing the amount of VOCs, and California is very active in this to decrease the amount of volatile organic compounds. Alcohol that they use in things like hairspray, for instance, even the alcohol is a contributor. It's not all just from transportation, it's from other personal care products as well. And then this forms uh, peroxyacetyl nitrate, and this and ozone. This is bad. It hurts the lungs. So all these things are damaging to humans, and this is a human health hazard. So these all need the sunlight, though. So this is known as photochemical smog, and they're the best way to get rid of it is a catalytic converter. That has greatly decreased the amount of photochemical smog. There are some things like it's best to fill your gas tank at night. If you have to fill it in the daytime, that's fine, but filling it at night is one way to reduce a simple activity like that is one way to reduce photochemical smog. But here is a picture showing that. And you can see here that the hydrocarbon emission changes with the daytime, and then you get the photochemical processes and these increase as you go on in the daytime. Oh, we've already talked about this. So catalytic converters is a good way to do this, and removes carbon monoxide as well. So what does a catalytic converter do? It causes complete combustion. It burns the carbon monoxide. Carbon monoxide is a fuel, and if you ever remember the fire safety videos, like if you before you open the door, if there's a fire in your house, feel around your doorknob. If the doorknob is hot, do not open the door. Why do they tell you that? Because if you open the door, you can have a bunch of oxygen flow in, and if there's an oxygen starved area of a fire, you're gonna have carbon monoxide there, which is a fuel, and there's heat, and you suddenly have an increase in oxygen. You can create what's called a backdraft, where it has an explosion. So carbon monoxide is in fact flammable, and you can burn it, and it does burn in a catalytic converter and gets rid of much of the carbon monoxide, not all of it. Unburnt volatile organic compounds also get burned in a catalytic converter, and as do the nitrogen oxides go down. So catalytic converters are wonderful inventions. If you ever touch one, they're hot because they're well, as the car is on, because it's burning stuff in them. Excuse me, I'm coughing. I'm talking. Okay, acid rain. We talked about this. That if it's below 5.6, and that's from the saturation of carbon dioxide, and then you can get acid rain from that. And we have pretty bad acid rain in Hawaii. I've measured it to be around a pH of 3. So it can get pretty bad here. But of course, like I said, we're used to it. So and acid rain, it's destructive to many things. It damages structures, and it causes a very bad effect on the biosphere. So, and the hydrosphere as well. Well, I guess part of the biosphere, if you will. It can damage the plant life, and it can damage the aquatic systems. Although water is the next chapter. Indoor air pollution is also important. So you can get worse, very bad pollutants at home. So if you use gas to burn things, you can get carbon monoxide and nitrogen oxides. Cigarette smoke is very bad. Also, kerosene heaters. We don't have to worry about kerosene heaters too much in Hawaii, fortunately. Mold also, so mold we do have to worry about. So this can cause an issue. And then ozone from whatever's using electronic equipment. This is a respiratory tract irritant. Cigarettes in general, they are bad. So cigarettes cause many different issues here. Radon, another thing we don't have to worry about in Hawaii. We don't have very much radon in our soil, and radon, we talk about this a bit with nuclear chemistry, and polonium 218 as well. That's a daughter product. That's a daughter nucleotide of radon. And ozone, it's an allotrope of oxygen, so it's another molecule that can form, which is oxygen. Ozone in the troposphere is bad. Ozone in the stratosphere is awesome, and it bothers you to breathe. I don't like the way it smells. It smells kind of bad. And it's the double-edged sword. So we need it. It's not in the mesosphere. It's in the stratosphere. We typically find it, but you can find it in the mesosphere too. But the stratosphere there, we get it's a UV shield, and well, and oxygen. So one of the points of this slide is that we will always have an ozone layer. As long as the sun is shining and we have oxygen in the atmosphere, we will have an ozone layer. But the problem is that we have uh, a hole in the ozone. So the chlorofluorocarbons, and ozone depletion is a natural process. But obviously, because it's part of how we absorb ultraviolet light. But if we have a catalyst that comes through and destroys it, it can decrease the amount of ozone and let more ultraviolet light through. And chlorofluorocarbons, this is a little out of date. This is not really how it works. It usually works via a surface chemical reaction with either volcanic ash or ice crystal, is where you typically see this. So it tends not to be a homogeneous phase. It tends to be a heterogeneous phase. This is relatively new knowledge, though. It's about 10 years old. I guess it hasn't trickled down into into this intro course yet, but it's a different process. It's a either using volcanic ash particulates or ice particles, and then the chlorine absorbs on the surface, and then that catalyzes the chemical reaction that way for ozone depletion. So CFCs certainly don't help. Okay, so many countries, we ban the use of CFCs, and we typically use I'm sorry, not chloro, fluorohydrocarbons is what's typically used now instead. And what's the problem with CFCs? They're so safe. They're such wonderful chemicals. I mean, you can drink them, you can breathe them. They're not going to bother you. They can displace oxygen, cause death that way. But they're really safe compounds. But we can use you can use sulfur dioxide, you can use ammonia as a refrigerant. These are all fine. But the thing is that if they're released, they present a very bad human health hazard. CFCs do not produce a very big human health hazard at all, with the exception of asphyxiation. And the problem is, though, is long term causes ozone depletion. So we've made some changes. So we've done fluorohydrocarbons instead. Problem is those can corrode some of the machine parts over time. So I guess you have to get a fridge more frequently now because of these. And there's an ozone hole over Antarctica, and it's if you've ever been to New Zealand, I love New Zealand. It's such a wonderful place. Uh, and for me, I can get a sunburn there very easily. So gotta slather on the sunscreen. So in the greenhouse effect is a wonderful thing. It warms the earth, and it's one of the reasons why life is possible here on Earth. Problem is, as anthropogenic activity has increased the amount of greenhouse gases to the atmosphere, and this shows here the effect of the greenhouse effect as it goes. And much of this, of course, is important, but the increase in greenhouse effect can cause changes to the environment. And here shows, notice it's not the annealing curve. This shows the temperature profile and the carbon dioxide concentration. So the uh, the y-axis here shows the concentration of carbon dioxide in parts per million. The x-axis is the year, and so the blue line corresponds to the left axis, and the temperature profile, temperature data is corresponding to the right axis. So you can see that there has been an increase in temperature over the past century. So, and as the Earth climate changes, there are impacts on food production, and where there are predictions of increases in infectious diseases. So, how are we going to mitigate global warming? We're looking at things, so emerging technologies, solar, nuclear. It'd be wonderful if we could get away from fossil fuels and do something like uh, nuclear fusion to get all our energy. So also carbon sequestration, so to grab carbon out of the air. These are answers. We're still working on them, so this is an ongoing problem, and we're looking to see if we can fix that. So, who pollutes, who pays? So the air. Well, in some ways, the air quality has greatly increased after President Nixon started to form the EPA and the subsequent Clean Air Acts in the 1980s. The air quality has greatly increased. So in fact, some have have suggested that the air is cleaner now than in medieval times. But this is starting to change as China and India become more industrialized. They are not held by the same standards as we are, and we as in the United States, and the pollution levels are starting to increase again. So we will see, and various things, pollutants have various effects, and have to be careful what we breathe in. So here are the uh, limits for air pollutants, and depends on which pollutant is what is allowed. And also here are the 7 primary air pollutants. So carbon monoxide, hydrocarbons, sulfur oxides, nitrogen oxides, sometimes called SOx and NOx. This is the SOx, NOx, and particulate matter, ozone, and lead. We don't typically put lead in our vehicles anymore. We used to put tetraethyl lead in gasoline, but that has been discontinued. And you really don't ever put tetraethyl lead into your car if you have a modern car, because that'll really poison your catalytic converter. The lead will complete. So don't like, ooh, it's a lubricant. I can use that instead. Don't do that. Like I said, it'll really damage your catalytic converter. And I know we don't have to worry about emission standards here in Hawaii, but other states you have to have your car tested for emissions, and that would be a costly repair. Okay, so this is the end of that, and next thing we will talk about is water.